Okay, so let's talk about amines, synthesis with amines. And while we're talking about amines, we'll also be talking about amino acids, because amino acids are an important target which introduce the amino group. So a lot of this is going to be reviewed because we've talked about various syntheses of amines throughout the course. They've just never been all in one place at once. So what do we already know about synthesis of amines? There are several methods you should already know where the product is an amine. How can you make amines, introduce amine? What can you make them from? Right, because often what we're interested in is a functional group transformation, so we want to know what functional groups we can start with and end up with amines as product, or amino acids as product. So one way we can do it is by reducing nitriles. And since you can make nitriles by SN2 substitution of alkyl halides, this is actually a way to get to amines from alkyl halides, but the amine will be one carbon longer. So for example, if we started with bromoethane and then treated that with sodium cyanide in some polar aprotic solvent to enhance the SN2 reaction rate, we would get propionitrile, right, having added a carbon. And then what is the reagent that reduces that to the NH2? This is limited to primary amines, right, because the nitrogen here doesn't have any hydrogens on it. So it's a way of making a primary amine from either an alkyl halide or a nitrile. But if you're making it from the alkyl halide, you're going to have an additional carbon in there from the cyanide. What's the reagent? H3O plus in water will hydrolyze the nitrile to a carboxylic acid. That'll actually be relevant as a way to make amino acids later. But this is not a hydrolysis reaction, this is a reduction. We have to add hydride. So this is lithium aluminum hydride in ether or THF, followed by your aqueous acid workup. So that's one functional group we can make it from, well, two, right, from the alkyl halide, as long as you don't mind having one extra carbon in there. Can we make amines from alkyl halides without adding an extra carbon? Your guess is yes. The answer is yes. How can we make amines from alkyl halides without adding that extra carbon? Or in other words, what nucleophile can we displace the halide with that can then be reduced to an amine? And the answer for that is sodium azide. So we started with that same bromide and treated it with NaN3. We would make the corresponding azide, which looks like that. And this will be reduced with lithium aluminum hydride under the same conditions. To make the amine. Also limited to primary amines because there's no hydrogen on the nitrogen of that displacement. And you'd usually use a polar electronic solvent, DMF, DMSO, something like that, so you get a nice SN2 reaction. It's not limited to the primary bromide, the way I've done it. Right? You could have some substitution at this point. Probably not tertiary, but you could do secondary. But the amine is an NH2 group in both of these cases. Can we just treat that with ammonia? Direct alkylation. What would happen? We treated this with ammonia. Is ammonia a good enough nucleophile to do that displacement reaction? Yeah, it sure is. But the problem is the product. Is still a nucleophilic lone pair. It's actually slightly more nucleophilic because now you've got an electron donating group, which is making this pair of electron more basic than NH3, which means it's almost impossible to stop at one alkylation. In fact, it's not so easy to stop at two alkylations because now you've got two electron donating groups that are making that lone pair even more basic, which means you're probably going to add a third. And now you have a lone pair that's still basic, so you're probably actually going to add another one. And make what's called a quaternary ammonium salt. So it's very hard to avoid overalkylation, multiple alkylation. If what you want is a quaternary ammonium salt, if what you wanted is tetraethylammonium bromide, this would be a fine way to do it, right? Just take ammonia and treat it with an excess of ethyl bromide and you just keep going. You can probably isolate some of the intermediate products where you've added one or two or three, but you're going to get a complicated mixture. It's much better if you're looking for a primary amine to make it indirectly with either the azide ion or the cyanide ion and then reduce it, rather than trying to do direct alkylation. The problem with those two methods, of course, is that they both involve using lithium aluminum hydride reduction. So if you have other groups in your molecule that are subject to reduction by lithium aluminum hydride, that's going to be somewhat problematic. So is there a way that we can introduce a primary amine without using cyanide or azide, and in some way that's going to avoid this overalkylation? And there is, it's called the Gabriel synthesis. And the Gabriel synthesis is also useful for amino acids. So what we're trying to do is we're trying to generate a nucleophilic nitrogen lone pair, but a nucleophilic nitrogen lone pair that will only want to alkylate once. If you take orthophthalic acid, 1,2-benzene dioic acid. And treat it with ammonia and heat the crap out of it. You will make phthalimid. Phthalimid should look a little bit familiar to you. It should look a little bit like the N-phenylmaleimide that you worked with or will work with. It's an imide. It's basically a diamide. This nitrogen lone pair is not basic. Because it's in resonance with the carbonyls. But this hydrogen is quite acidic. Because it's between two carbonyl groups. Do anybody remember what the pKa of a amide is, an amide hydrogen? It's significantly lower than a CH2 next to a carbonyl, which would be about 20. It's a little higher than that. It's more like 15, 16. But obviously here now, because it's between two oxygens, it's even more acidic than that. So this can be removed with a relatively mild base. You can actually treat it with bicarbonate ion. And the bicarbonate ion will take that proton off and convert it to a resonance stabilized anion. Right? And we can write resonance structures that have that negative charge delocalized out onto the two oxygens. I'll just show one of them. But obviously you can write another one that puts it on the other oxygen. So we exploit the fact that we have an acidic hydrogen there. This is nowhere near as basic as an amide ion would normally be, which means that you can alkylate it productively. It's a nice SN2 substrate. And that lone pair is not basic for the same reason it wasn't basic before you removed the proton with sodium bicarbonate. So you don't have to worry about over-alkylation, right? There's going to be no additional alkylation. Now all you have to do is figure out how to hydrolyze these two bonds, and you can generate the primary amine. So it's another way to get primary amines. And the other product depends on what you have used as your workup. A reagent that's commonly used to cleave those is hydrazine. Hydrazine is quite basic. It's got two basic nitrogens in it. And the other product will be this six-membered ring containing two nitrogens and a primary amine. So the Gabriel synthesis generates primary amines. It's basically direct alkylation, but it's direct alkylation with a modified nitrogen that doesn't have the ability to add a second alkyl halide. So if I asked you for the mechanism of that reaction with the hydrazine, where would you start? This reaction will actually come back again when we do peptide synthesis, because hydrazine is also a reagent used in determining the identity of the C-terminal amino acid. Of peptides. And if you understand this mechanism, then you also understand how this works in determining the identity of the C-terminal amino acid in peptides. Remember Sanger's reagent, which was that fluorodinitrobenzene that we talked about, as a way of determining the N-terminal amino acid of a peptide by tagging that N-terminal one with a UV active and fluorescent group. This is a way of determining the C-terminal amino acid. And the mechanism is basically the same. So what would you do if it were Thursday morning and this was on the exam? We can start the exam early again in case you have a class right after this. So I'll try to be here by 7:15-ish on Thursday morning. So what you always do when you're trying to determine a mechanism, and this will also be true of your reactions for your group projects, is you try to identify where the electrophiles are and where the nucleophiles are, and then get the good nucleophile together with the good electrophile. And it's often productive to draw minor resonance structures, because the minor resonance structure often gives you an idea of what the charge separation looks like within the molecule. So if you draw the minor resonance structures, and there are several minor resonance structures, sometimes you can identify the electrophile where you don't necessarily see it in the regular form, right? The minor resonance structure always tells you something about the reactivity. That's great rule of organic chemistry number 1. I guess great rule of organic chemistry number 1 is know how to draw good Lewis structures. That's something you have to know. So, where's the best electrophile in the system? The carbonyl carbon, right? Carbonyl carbon is the best electrophile. Where's the best nucleophile in the system? Probably the hydrazine, right? This NH2 lone pair. So what we want to do is get together the best nucleophile with the best electrophile, right? It's like morphine reacting with T-butylacetoacetate, right? Carbonyl group is the electrophile. The nitrogen lone pair is the nucleophile. The other NH2 group is just watching for now. What's next? This is starting to look like a nucleophilic acyl substitution, right? We've had the nucleophilic attack, step 1. What is step 2 of a nucleophilic acyl addition? And under basic conditions like this, it's usually a crap leaving group. It's less of a crap leaving group this time than usual, though. Because this anion is resonance stabilized. Hydrazine will cleave any amide. including the peptide bonds in your protein. So if you treat a protein or a peptide with hydrazine, it will cleave all of the amides, but it will not react with the negatively charged C-terminal carboxylate group, which means it will convert every amino acid except the C-terminal group into the hydrazide, and then you have one free amino group that's much more polar, and that's how you can determine the C-terminal amino acid. What's next? Putting my charge on the nitrogen, it has 4 bonds, that's next. Proton transfer is next. I'm going to show it intramolecularly because why not? It'll take a proton of whatever it collides with first. To generate an intermediate that looks like that. Now what? Oops, I lost the couple. That's still there. Now what? Well, let's just do it again. These are not basic because they're resonance. But this one is. So that can then just come through and attack this carbonyl group. Right? And we're doing the same step, nucleophilic attack. And since it's an intramolecular reaction, it is probably occurring at a pretty good rate. Keep dropping the CH3. That group is still there. Hold on, that's not right. I ran out of space. I need more space to write that intermediate. There, better. 6-membered ring. So it's the same thing, right? Nucleophilic attack, loss of leaving group. That's going to cleave your amide bond. And generate the product. Well, at least after a proton transfer, the product. And in this case, that leaving group is terrible, but we can promise it this proton in the last step. So that will be favorable. So we've got the nucleophilic attack, which is step 4, actually. And then we've got the loss of the leaving group, which is step 5. And then our last step is that proton transfer. So it's just 2 successive nucleophilic acyl substitutions where a nitrogen lone pair of hydrazine cleaves an amide bond. Nucleophilic attack, loss of leaving group, proton transfer, and then a second nucleophilic attack, loss of leaving group, proton transfer. You don't have to use hydrazine. You could also cleave this with aqueous base, right? Because we know that amides can be cleaved with aqueous base. And if you cleaved it with aqueous base, the product would be the corresponding diacid, which is what we started with anyway. But hydrazine is a nice reagent to do it with. It's a little milder than treating this with KOH and water. So you don't have to worry as much about side reactions in the rest of your amine. But if you wanted to just do an ordinary base catalyzed hydrolysis, that would work too. You can even do acid catalyzed hydrolysis. Amides can be cleaved with acid, base, or hydrazine. The hydrazine is the mildest of the three methods for cleaving that. So this mechanism is something that's not new. It's just review. It's a way of making primary amines. The Gabriel synthesis is a way of making primary amines. You may remember the malonic ester synthesis, where we started with like a malonate. If you start with a bromomalonate like this, the Gabriel synthesis can be used to make primary amines. And thus primary amino acids. So we can start with phthalimid and NaHCO3, make the anion and displace the bromide. Does anybody remember approximately what the pKa of that hydrogen is on the malonate sandwiched between two ester groups like that?
I want to say 14, but that's
It's close. If this nitrogen group weren't there, it would be 13. Because that nitrogen group is there, and that's an electron withdrawing group, it's actually probably a little bit less than 13 now. But it's certainly something that can be removed easily. So if we treat that with base, we can make the corresponding anion. Which can then be alkylated. So let's say we're going to treat it with that, doing SN2 displacement. Lots of atoms. Right, so we've now alkylated it, and if we treat this with aqueous acid and heat it up a little bit, we would get out carbon, yes. I'm going to redraw that somewhere where there's actually space to draw it. Right, so this is an alpha amino acid. It's actually closely related to methionine. It's basically methionine with an extra carbon. How does that happen? How does that big ugly mess here magically become the amino acid? Right, this part is intact, right? That's just along for the ride. So our alkyl group, right, this carbon is the alpha carbon, that's here. We kind of mark our carbon and follow it around. That carbon's there. Here it is throughout the process. What's going on?
Did you redraw that bottom one somewhere else? I'm confused.
This is this. I just redrew it where there was space to show the whole thing so the NH2 group didn't get lost. NH3 group. Here, I'll get rid of it from here so you don't see it twice. This arrow goes all the way over here. So we're basically cleaving that bond and that bond and that bond. And that bond. And in fact, that one too. So we're cleaving a ton of bonds. This all happens in one reaction pot, but let's look at it stepwise. Let's hydrolyze the two esters, because in aqueous acid we know that esters hydrolyze. So if you wanted to show that mechanism, right, acid catalyzed ester hydrolysis, that would be 12 steps. We're not going to show that. But it would be 6 steps to do the reverse Fischer esterification on one, and then another 6 steps to do the reverse Fischer esterification on the other to cleave those two esters. And now we're going to do amide hydrolysis, right? We're also going to hydrolyze the amide on both sides in aqueous acid. And that's another 12 steps. Right? 6 steps to cleave the one, 6 steps to cleave the other. And liberate NH3 group. Right, so we've cleaved 4 carboxyl groups, 2 esters and 2 amides, to generate that intermediate. But you'll recognize that as a beta diacid, right? If we focus on this carbonyl group as the ground zero, This is a beta diacid. And you know beta diacids are unstable. And will break down if I redraw it like this. That will break down to pull that hydrogen off and lose CO2 gas. Which was one of the steps in the malonic ester synthesis. Once again, I run out of board. And then all you have to do is a proton transfer step to put the hydrogen on the alpha position. Right, this is now tautomerization that is necessary. Oops, sorry, that's another way to get there. Give the product. So those are all reactions you've seen before. It's just a lot of them happening all at once, right? Ester hydrolysis cleaving this bond and this bond, then amide hydrolysis cleaving this bond and this bond, and then loss of CO2 cleaving this carbon-carbon bond. So it's a useful amino acid synthesis because the intermediates are all pretty stable, and we don't have to worry about multiple alkylation steps. Now's a good time to take a break, I think, and then we will talk about intercepting imine ions on the way to amines.